Okay, today let's have a look at the fourth lesson of Chapter 5, Standard Enthalpies of Formation, and then present and future energy sources. Sulfur dioxide gas, SO2, is a colorless, odorless air pollutant. The majority of atmospheric sulfur dioxide gas comes from the combustion of fossil fuels containing sulfur impurities, such as those produced in coal-burning power plants, which is shown here in Figure 1. Once in the atmosphere, sulfur dioxide undergoes further chemical reactions to form acid precipitation, which can cause significant damage to aquatic ecosystems. In addition to having other negative effects on the environment, an important step in the production of acid precipitation is the reaction of sulfur dioxide with oxygen to produce sulfur trioxide. The balanced chemical equation for the formation of 1 mole of sulfur trioxide gas is illustrated in the equation on top. Measuring the enthalpy change of this reaction in the laboratory is difficult because the sulfur compounds are toxic. However, the enthalpy change can be calculated using Hess law and the following thermochemical equations. Which are illustrated here. Applying Hess law, equation 1 remains unchanged because sulfur trioxide gas is on the product side. Equation 2 is reserved so that sulfur dioxide gas is on the reactant side, resulting in equation number 3 here. Therefore, the enthalpy change for the production of sulfur trioxide gas is negative 144.2 kilojoules. Equations number 1 and number 2 are formation equations and represent the formation of a compound from its elements. Okay, so next let's have a look at the concept of standard enthalpy of formation. The standard enthalpy of formation of a compound is a change in enthalpy that occurs when 1 mole of compound is formed from its elements, with all substances in their standard states. A substance is in a standard state when it's in its most stable form at SATP. SATP stands for standard ambient temperature and pressure, which is usually 25 degrees Celsius, 100 kPa. Figure 2 here shows oxygen, sodium, and mercury, each in their standard state. Most elements are solids in their standard state. However, the standard state of the noble gases, as well as of the diatomic elements hydrogen, oxygen, nitrogen, fluorine, and chlorine, is the gas state. The standard state of bromine and mercury is the liquid state. The standard state for a substance in solution is at a concentration of 1 mole per liter. The degree sign on the symbol, delta HF degrees, indicates that the process takes place under standard conditions. The standard enthalpy of formation of an element in its standard state is always 0. A value of 0 is assigned since an element is in its most fundamental form at standard conditions. Thus, the standard enthalpies of formation of oxygen gas, solid sodium metal, and liquid mercury metal, for example, are all zeros. So consider the thermochemical equation for the formation of nitrogen dioxide gas from its elements in their standard states, which is illustrated in this equation here. Like all standard enthalpy of formation equations, this standard enthalpy of formation equation shows the formation of one more of the product. The formation of nitrogen dioxide gas from its elements is endothermic, absorbing 33.2 kilojoules per mole from its surroundings. Enthalpies of formation may be either exothermic or endothermic. You can have a look at these values listed in table 1. This table lists standard enthalpies of formation for several compounds. I also hand out this form to you before this class, right? Okay, next, let's have a look at how we can use standard enthalpies of formation. We try these values listed in this table to calculate enthalpy change. So as table 1 here provides the standard enthalpies of formation for many pure substances, we can use these values to calculate the standard enthalpy of reaction for many chemical reactions. Consider the combustion of methane gas, CH4, represented by the balanced equation, which is shown here on top left. Figure 3 illustrates one possible pathway for the combustion of methane. In this pathway for the combustion of methane, the reactants are broken down into their constituents, elements in reactions A and B. The elements are then used to synthesize the products in reactions C and D. In reactions A and B of the pathway shown here in figure 3, the reactants are decomposed into their elements. In reaction A, methane is broken down into elemental carbon and hydrogen gas. The balanced chemical equation for this reaction is shown here on top right. And the equation above is the reverse of the formation equation of methane, which is shown here in the second equation after that. From table 1 here, we know that delta HF degree for the formation of methane is negative 74.4 kilojoules per mole. Since we change the sign of delta H whenever we reverse a reaction, so here delta H degree for the decomposition of methane into its elements then is positive 74.4 kilojoules. Oxygen gas exists in its elemental state, O2. It cannot be broken down further. No energy change occurs. In reaction C and D of the pathway shown in figure 3, the elements from the decomposition of reactants combine to form the final products, carbon dioxide and water. The balanced chemical equations are shown here. These two reactions. Since 2 mole of water is formed in the combustion of methane, the delta HF degree of water must be multiplied by 2, as the following two equations shown here. So the change in enthalpy for the reaction is the sum of these values, which gives us negative 890.7 kilojoules. So the use of standard enthalpy change. The use of standard enthalpies of formation to determine the enthalpy of combustion of methane is summarized in Figure 4. The decomposition of methane gas into its elements is an endothermic reaction. However, when elements combine to form products, a large quantity of energy is released. Since only the standard enthalpy of formation values were used in this example, we can state the following simplification. The enthalpy change for any reaction can be calculated by subtracting the sum of the enthalpies of formation of the reactants from the sum of the enthalpies of formation of the products. The enthalpies of formation are multiplied as indicated by the balanced equation, which is shown here on the bottom of this page, where sigma means the sum of terms and N products and N reactants represent the amount in moles of each product or reactant respectively. And of course, using this equation, the change in enthalpy for the combustion of methane gas is calculated to be negative 890.7 kilojoules, right? Which agrees with the value we obtained previously. And this calculation is shown on the right side of this page. You can have a look at this by yourself. Okay, so next let's have a look at a sample problem which illustrates how we can calculate enthalpy change of a reaction delta H using standard enthalpy of formation values and table 1 here. Okay, let's consider this problem. Using standard enthalpies of formation in table 1, calculate the standard change in enthalpy for the thermite reaction represented by the balanced equation here. Okay, I'll give you some time to consider this question by yourself, and after that we can have a look at the solution together. Okay. Alright, let's have a look at the solution together. So first of all, from table 1 we can check the standard enthalpy of formation for each of the substances involved, right? And according to this formula on the bottom, we can calculate the standard enthalpy change for the thermite reaction, which is negative 1375.7 kilojoules minus minus 824.2 kilojoules, and the final result is negative 851.5 kilojoules. Therefore, the standard enthalpy change for the thermite reaction is negative 851.5 kilojoules. So have a look at the process here. Make sure you're able to solve this by yourself, okay? Okay, if you don't have any question, let's have a look at the next one. Until recently, liquid methanol was used to fuel high-performance engines in race cars. Gasoline is a mixture of hydrocarbons, but assume for this problem that gasoline is pure liquid octane, which is C8H18. Use the data in Table 1. Determine the standard enthalpy of the combustion per gram of A, methanol, and B, octane, and then determine which fuel is more efficient in terms of the amount of energy released per gram. And you are also given the balanced chemical equation for the combustion of methanol and octane respectively. Okay, try to solve this by yourself, and then we can have a look at the solution together. Okay, your task is to find the amount of energy released per gram of methanol and octane respectively, right? And compare which value is larger. Alright, let's have a look at the solution together. Okay, first of all, we know the standard enthalpy change of combustion of 1 mole of methanol is calculated in this way, right? According to the chemical reaction formula given to us, you can divide both sides using coefficient 2, and then that number is negative 726 kilojoules per mole. And the molar mass of methanol is also needed. So using the molecular formula of methanol, we can easily calculate its molar mass, which is 32.05 grams per mole. Then the standard enthalpy change of combustion of 1 gram of methanol is given by this number, negative 726 kilojoules per mole divided by 32.05 grams per mole, which is negative 22.65 kilojoules per gram. This means the combustion reaction of 1 gram of methanol releases 22.65 kilojoules energy, right? And using the same method, we can also calculate the combustion reaction of 1 gram of octane releases how many amount of energy, right? So following the same method, we can easily find the combustion reaction of 1 gram of octane releases 47.87 kilojoules energy. And if you compare these two numbers, you can easily see that octane is more efficient in terms of amount of energy released per 1 gram, right? Alright, if you finished, next let's have a look at the second half of this lesson. We're going to discuss present and future energy sources. How we supply our energy needs now and how we will supply them in the future are among the most complex and challenging issues of our time. Every energy source and energy technology, both conventional and alternative, has costs and benefits related to its availability, sustainability, and impact on ecosystems, the climate, economics, and politics. Okay, first, let's have a look at conventional fuels. Conventional fuels are fuels that commonly used today. These include organic fuels such as wood or straw, fossil fuels such as coal, petroleum, and natural gas, and nuclear fuels such as uranium. Conventional fuels have been in use for a long enough period that we have systems in place to find, process, and deliver these fuels where they are needed. For example, petroleum may be pumped from beneath the Earth's surface on an oil platform, which is shown here in Figure 1. It's then carried by pipelines or ships to a refining plant, where it's processed into useful petroleum products for everyday use. Wood is perhaps the most widely used conventional fuel. Wood is a renewable fuel source since we can plant trees to replace those we burn or use to produce charcoal. A wood-driven fuel Unfortunately, the rate at which we use wood is much faster than the rate at which some species of trees renew their populations. Carbon dioxide is a natural product of wood and charcoal combustion, and its effect as a greenhouse gas must be considered. Fossil fuels. The most widely used class of fuel today is fossil fuels, namely petroleum or crude oil, coal, and natural gas. The energy stored in fossil fuels originated in the sun. Through the process of photosynthesis, captured solar energy is converted to chemical energy by plants. Fossil fuels form from the decaying remains of plants and animals, which are then subjected to high temperatures and pressures beneath Earth's surface for thousands of years. Petroleum is a thick, dark liquid that is a mixture of hydrocarbons. Crude petroleum is not used as fuel directly. It's first refined. Refining petroleum is achieved by fractional distillation. This process takes advantage of the differences in boiling points among the different hydrocarbons in crude petroleum. The composition of crude petroleum varies, but it consists most of these straight-chain hydrocarbons between 5 and 25 carbon atoms in length. When petroleum is heated, the smaller molecules enter the vapor state first, and then, while the larger molecules remain in liquid form. The smaller molecules have lower boiling points than the larger molecules because they have relatively weaker intermolecular forces. The different hydrocarbons are then collected into fractions by selective condensation at different temperatures. Each fraction contains hydrocarbons with a specific range of chain length. Here, Table 1 shows some common uses for different petroleum fractions. Hydrocarbons have many uses other than as fuels, such as in the manufacture of pharmaceuticals and plastics. Natural gas is another type of fossil fuel. It's usually found with or near petroleum deposits. Natural gas is mostly methane gas, or CH4, but it also contains significant quantities of other hydrocarbon gases, such as ethane, propane, and butane. Natural gas is primarily used for heating buildings, Coal is a fossil fuel formed from decaying plant matter that has been buried for millions of years. Plant material is composed primarily of cellulose, a carbohydrate. Deep beneath Earth's surface, plant matter is subject to high pressure and temperatures. Over time, these conditions cause chemical changes in cellulose, removing a large portion of the oxygen and hydrogen items and leaving mostly items of carbon. There are 4 types of coal, which are classified based on their carbon content. In the past 20 years, Canada and most other countries have become highly dependent on fossil fuels. Fossil fuels form at a far slower rate than we consume them. So fossil fuels are not renewable. Fossil fuel deposits are limited in supply, and many, such as Alberta's oil sands, are difficult to process. Combustion of fossil fuels has damaging environmental consequences. Therefore, scientists, engineers, and entrepreneurs are working to find new sources of energy. The combustion of all fossil fuels produces carbon dioxide gas and water vapor, which are released into the atmosphere where they contribute to global warming and climate change. Climate change leads to loss of species due to changes to habitats and also cause more floods, droughts, fires, and disease. Other pollutants are also released when we burn fossil fuels. For example, the combustion of coal that contains high quantities of sulfur releases sulfur dioxide gas. When sulfur dioxide gas combines with water in the atmosphere, sulfurous acid is formed, which falls as acid rain. Extracting and transporting fossil fuels can be dangerous as well. For example, in 2010, a deep-water oil well exploded in the Gulf of Mexico and leaked oil into the ocean for almost 3 months before the well was successfully capped. The environmental, social, and economic damage was extensive. Okay, next let's have a look at nuclear energy. Nuclear energy is a conventional energy source that is not subject to most of the disadvantages of fossil fuels. Nuclear energy is not a limited resource, and it does not involve the release of greenhouse gases. There are two types of nuclear reactions by which nuclear energy may be released: fusion and fission. Fusion is not currently used to generate energy on Earth. Nuclear generating plants instead use fission, which releases extremely large quantities of energy compared with chemical reactions and physical processes. Uranium-235, the primary source of nuclear energy used in fission, is also relatively inexpensive. Nuclear power plants produce substantially less air pollution than electrical generating plants fueled by the combustion of coal. However, there are serious disadvantages to nuclear power generation. Nuclear power stations are expensive to build and maintain, and the used fuel rods, although no longer useful in a power plant, are still highly radioactive. This nuclear waste must be properly stored to prevent radioactive radiation from entering the environment. But a safe, long-term storage solution has yet to be found. During the transformation of nuclear energy into electrical energy, vast quantities of water are used to keep the nuclear fuel rods from overheating. This is why nuclear power plants are built close to a water source. Much of the thermal energy absorbed by the water from the fuel rods enters the environment once the water is returned to its source. This can increase the water temperature significantly and can cause a decrease in the quantity of oxygen and other gases dissolved in the water, which can have negative consequences for aquatic life. Perhaps the greatest concern with nuclear energy generation is the potential for the accidental release of radiation. Research continues that is aimed at improving safety, but many believe nuclear power can never be safe. Alternative energy sources. As we deplete our fossil fuel stores and as our energy demands increase, ongoing research is focused on identifying and developing reliable new sources of energy. Some of these use renewable natural resources such as wind, solar radiation, and tides. Others involve alternative fuels such as synthetic fuels, hydrogen gas, and biofuels. A separate but related goal is to develop ways to produce energy that will be environmentally friendly. Some alternative energy sources are much more environmental friendly than others. So let's have a look at some alternative energy sources. First, synthetic coal-based fuels. A synthetic fuel is any fuel that is artificially formulated and manufactured. In other words, it does not appear naturally, or at least not in usable quantities. Coal is a starting point for two synthetic fuels. The simplest artificial fuel made from coal is coal slurry, which consists of pulverized coal mixed with water. Coal slurry can directly replace petroleum-based fuels in some cases. For example, coal slurry can be used directly in an oil furnace as fuel. Coal contains large hydrocarbon molecules that are either solids or thick liquids at SATP. These molecules cannot be transported through pipelines, which limits their usefulness. Chemists have developed a process called coal gasification that reduces the size of these molecules and then converts the coal to gaseous fuel mixture. During coal gasification, coal is first mixed with oxygen gas and steam at high temperatures. This breaks many of the carbon-carbon bonds in a coal. Then new carbon-hydrogen and carbon-oxygen bonds form when the smaller molecules react further with oxygen gas and water vapor. The final product is a mixture of carbon monoxide gas and hydrogen gas called synthetic gas, or syngas. The balanced equation for the production of syngas is illustrated here on the right side. Another useful fuel, methane gas, CH4, is also produced during coal gasification. Since syngas is derived from coal, the environmental costs with respect to mining the coal still exist, as do the greenhouse gas concerns. On the positive note, the use of syngas as a fuel source is more energy efficient than burning coal directly. Okay, next, another possible alternative energy source, hydrogen gas fuel. Hydrogen gas can be utilized as fuel source. Hydrogen gas has a high enthalpy of combustion, releasing about 2.5 times the quantity of energy per gram that is released by the combustion of natural gas. The thermochemical reaction of the combustion of 1 mole of hydrogen gas is illustrated here on the bottom. The only product of hydrogen combustion is water vapor. The widespread use of hydrogen gas as a fuel has 3 main limitations: production cost, storage, and transportation. Hydrogen gas can be produced by passing an electric current through water in a process called electrolysis. Electrolysis breaks a bond in water molecules, forming hydrogen gas and oxygen gas. The quantity of energy required to form 1 mole of hydrogen gas by electrolysis of water is negative 285 kilojoules, the same amount released by the combustion of 1 mole of hydrogen gas. Hence, with respect to sustainable energy production, we are not ahead. We put in as much as energy in order to produce hydrogen gas as we extract when we combust hydrogen gas. In addition, even though our oceans contain an almost endless supply of water, large-scale production of hydrogen from water is not that economically feasible, because the cost of electricity is too high. Hydrogen fuel is therefore far too costly to be widely used at this time. Hydrogen gas is also difficult to store and transport. Tankers and pipelines used to transport fuels are generally constructed with metal. Molecules of hydrogen gas are able to infiltrate the metal lattice structure, making the metals brittle. Brittle metal is likely to fail, which would allow hydrogen fuel to leak out. Since hydrogen is so flammable, a hydrogen leak could easily result in explosion. Okay, another type of alternative fuel source is a biofuel. Biofuels are fuels that are derived from living things or biomass. For example, wood can be considered a biofuel. Liquid biofuels have much applications than solid ones. The most widely known liquid biofuel is ethanol. A number of companies and researchers think that ethanol could supplement or even replace gasoline. Most ethanol is produced by fermenting sugars, a process that produces liquid ethanol and carbon dioxide gas. Various sugars from different sources can be fermented to produce ethanol, but corn is the most commonly used source of fuel-grade ethanol in North America. Corn kernels store large quantities of starch, carbohydrate formed from long chains of glucose molecules. To make ethanol biofuel, enzymes are first added to ground corn kernels to break the starch down into sugar molecules. Yeast is then added to the sugar mixture. The yeast cells carry out fermentation to obtain energy from the sugars. The end products of fermentation are liquid ethanol and carbon dioxide gas. However, the final mixture will still contain yeast and small quantities of the reactants. The mixture is heated to kill the yeast cells, and this causes the liquid ethanol to change state to ethanol vapor. The pure ethanol vapor is then captured and condensed to ethanol liquid. A fuel can burn in an internal combustion engine only when it's in the vapor state. Ethanol is not as volatile as gasoline. That is, it does not vaporize as readily and therefore cannot be used directly as a fuel source in most automobile engines. Alternatively, gasohol, a solution of about 10% ethanol in gasoline, will burn in most engines. Another ethanol-based biofuel, E85, is 85% ethanol and 15% gasoline. E85 can only be used in vehicles with specially designed engines. Methanol is another alcohol-based biofuel. Methanol has been used as a fuel in some race cars for many years. Research aimed at using methanol as a fuel for conventional automobiles is still ongoing. The main advantage of biofuels over fossil fuels is that they are produced from renewable sources or living plants. Biofuel production involves the use of fossil fuels in farm machinery, transportation, and the manufacturing of biofuels. Although much less petroleum is used than in the production of gasoline, the combustion of biofuels releases the same greenhouse gases as fossil fuels, but the gases are carbon neutral, since the carbon is absorbed from the air. In addition, biofuel combustion releases 10 to 15% fewer greenhouse gases than fossil fuels. Using plants such as corn for biofuels may also increase the cost of food and reduce our food supply at a time when Earth's population is over 7 billion. Land that was once used for producing food for humans is now being used to produce crops to be converted to biofuels. Finally, environmental costs such as soil erosion have yet to be quantified. Okay, let's have a look at energy efficiency. The efficiency of a device or system is a ratio of useful energy produced to the total amount of energy expended. Efficiency is normally calculated as a percentage. The efficiencies of various energy resources for electricity generation, industrial processes, transportation, and heating vary widely. For example, generating electricity using hydropower or hydroelectricity is around 85% efficient. The efficiency of electricity generation using fossil fuels, nuclear reactions, wind, biofuels ranges from 35 to 45%. Current solar masses have an efficiency of around 15%. The readily accessible non-renewable sources of energy are quickly running out. Unfortunately, our current renewable sources of energy are inadequate to satisfy the demand. Conservation is one approach to meet the demand for electricity energy. To conserve energy, newer devices are designed to use less electrical energy than older ones. For example, some appliance manufacturers claim that replacing a 20-year-old refrigerator with a modern, energy-efficient unit can save over $100 each year on your electricity bill. In fact, some municipalities offer free removal services to encourage their citizens to update their appliances. We also can help meet our energy demand by improving the efficiencies of power plants. Okay, so this is the end of today's lesson. Also, we have completed chapter 5. If you don't have any questions, I'll see you next time. Bye.